Okay, so we are now going to prove the second half of the theorem of that chapter. So this is that if G is the output hypothesis in our pack learning framework, then we had to bound the generalization error. And we did not want to use the union bound and so on. So the bound that we will prove is that E in of G minus E out of G greater than epsilon is less than or equal to 4 mh of 2n e to the minus n epsilon square by 8. This is what we will prove now. That the probability that the training error and the test error, when G is chosen in any adaptive way, you could use any favorite learning algorithm, gradient descent, brute force search, any method you like, EM algorithm. The difference between the training error and test error, provided G is restricted to the hypothesis class H, is upper bounded. The probability this is greater than epsilon is greater than this. For mh of 2n, where mh is the growth function associated with the hypothesis class H, times e to the minus n epsilon square over 8. So this is what we will prove. This is very similar in spirit to the union bound we had before for the case of finitely many hypotheses. The constants are slightly different. There we had 2. Here we have 8 in the denominator. There we had 2 in the numerator. There we also had 2 instead of 4. And m was, instead of mh, instead of the growth function, we had m, the total number of hypotheses. So this particular proof will be sort of extended, be an extension of the proof we did for the union bound argument, carefully done so that we can rigorously incorporate the growth function and get the right constants here. But you will see how delicate the arguments are. Some of the arguments are extremely delicate in this proof. But before we do that, we will discuss some implications. Since mh of n is a polynomial in n, whenever the VC dimension is finite, the right hand side will go to 0 as n goes to infinity. So as you have a large number of samples, this quantity is decreasing exponentially in n. This quantity is increasing polynomially in n, so the product will go to 0, which means that the probability that the training error and test error are greater than any threshold epsilon can be made arbitrarily small if you have sufficiently many samples, which means that learning is possible in this regime. If you have lots of samples, you can actually generalize. So this is the first fundamental theorem in learning, that because you don't know, you are given some training samples, how do you know you will do well on test samples? This gives a guarantee, a rigorous guarantee that you can generalize from training error to test error. And let's do the same sort of calculations we did for the union bound result. So let's say delta be this quantity. So 1 minus delta is known as the confidence level. Okay. Then since mh of n is less than n to the dvc of h plus 1. Okay, this is the growth function. We showed this from the previous theorem. And we can just approximate this as n to the dvc of h if n is much larger than 1. The plus 1 is a constant. It won't have much effect. So just for the sake of calculations, we will ignore it and we'll approximate this as n to the dvc. Then through simple algebra, what you get is that epsilon is square root of 8 over n log 4 times n to the dvc of h by n by delta. And this scales as square root of dvc of h by n times log n over delta. So if you look at this quantity, so what you're doing is your delta is this quantity. You can substitute for mh. Mh of n is upper bounded by this, so mh of 2n is just 2 to the n dvc plus 1. And we'll ignore the plus 1 for simplicity, it won't change anything if n is large. And then when you substitute that expression here and solve for epsilon, you can get this quantity. Okay. Then if you look at this quantity, you have log n to the dvc. So you can bring dvc outside the log, you can ignore the constants. So you get a scaling like dvc over n times log of n over delta. This is what epsilon is. Okay. So what this is saying is that this epsilon is scaling as square root of dvc by n and times the logarithmic factor, like log of n by delta. So what we can say is now that with probability greater than 1 minus delta, our generalization error will be less than the training error plus some constant omega. Omega is the penalty term, which scales as theta of dvc by n log n over delta. So higher the VC dimension, higher our penalty term will be. We'll have to be more conservative in giving a bound on the generalization error. The more samples we have, this quantity will decrease like square root of log n by n for a fixed delta. And so if we were to look at, say, if we were to fix n and try to study different hypotheses and look at how the generalization error and how the test error will behave, then let's sketch dvc of h here. So we are fixing n and we are always fixing delta. So as you have increased the VC dimension, you get more and more complex hypotheses. So the linear hypothesis is here. Maybe some polynomial hypothesis is here, third order perhaps. A neural network might be here. Depending on the depth, you might have a certain VC dimension. So the point is, as you increase the VC dimension, you are allowing for a more complex hypothesis class. Here we have fixed number of samples. Maybe we have 100,000 samples, that is fixed. Now as you make the VC dimension more complex, your training error will look like this. This will be E in of G. The training error will improve as you make your hypothesis class more complex, right? If you have a linear hypothesis, you won't be able to fit as well. If you use a very deep network, you'll be able to fit on the training data better. So as you go along this dimension, as you have more higher VC dimension in general, your training error will continue to decrease. Now the quantity omega will, however, increase with the VC dimension. Okay? If you look at omega for a fixed n and delta, it's going to increase as square root of dvc. So omega is going to increase like this. And now E out is essentially the sum of the two quantities. So E out might look like this. So if you look at E in, it is decreasing with dvc. Omega is increasing, E out is bounded by this. So E out will initially decrease as you make your hypothesis class more complex, but later on the penalty from generalization will kick in, and you will end up sort of not doing as well. So here you have too rich a hypothesis class, so you do well on the training data, but you will not generalize well. This is known as overfitting. Okay? This part here is the opposite case. Here you simply have a very simple hypothesis class. So your training error is large, but your test error will be close to training error. This is known as underfitting. You haven't selected the right hypothesis class for your problem. You have too simple a model that does not capture everything about the training set. And this is ideally the ideal hypothesis class you should select, where the training error is small and the generalization bound doesn't hit you much, and so you will be doing better. So that is, so you want to minimize the test error by operating somewhere between too simple a hypothesis and too complex a hypothesis. So this is the main implication. The VC dimension, if it is of the right order, it will balance between the underfitting extreme and the overfitting extreme. Any questions? Oh, battery. So that we save the video and found the charger. Okay. Any questions? Okay, so you can continue with the proof now. So we saw from previous discussion in last lecture, when we were deriving the union bound for finite hypothesis case, we were interested in probability that E in of G minus E out of G is greater than epsilon. This is the quantity we are interested in bounding. And we argued that this is less than the probability of the union over all hypothesis of the event that E in of H minus E out of H is greater than epsilon. This is what we saw last lecture, that if this quantity, if there is a bad event with the output hypothesis, at least one of the original hypothesis H should have the bad event. So if there is a training data set for which E in is too small but E out is large, which makes this a bad event, then that same training set should induce a bad event for one of the hypothesis class in H. Right? That same set of training points will have E in to be small and E out to be large for one hypothesis H. This is what we argued last lecture. And then we went on and developed, applied a union bound here. We took this, we said this is a union of events. We upper bounded this by the union bound, and that's how we were able to complete the proof for finitely many hypotheses. We'll continue that same, this will continue onwards from this step in the proof of this theorem. So this will be taken as a given. Any questions about this? This is one of the key steps we'll be building upon, which was discussed in the last lecture. Okay. So if you look at this particular event, if you look at En of H, it is 1 over n summation of n going from 1 to capital N, E of H of xn and yn, right? E is the error function. H of xn is the evaluation of H on this data point. Yn is the true label, and this is a definition. This depends on H only through H of x1, H of x2, up to H of xn. So if I had to compute the training error, all I need to know is the dichotomy vector generated by H. Because if I know the dichotomy vector, I just plug it in here, and then I compare it with the ground truth, the true labels, and then I get the average number of errors. So if two hypotheses H1 and H2 had the same dichotomy vectors, they would have the same value of En. So at least as far as En is concerned, we don't need to take union over all the elements in H. We just need to consider how many distinct dichotomy vectors there are, because those will be the different values of En that will be generated. If I have two vectors, two hypothesis class that are generating the exact same dichotomy vectors, I'm clearly double counting in the union bound, because En is going to be the same quantity. So as far as En is concerned, let's say this was 1, for example. Let's say we don't think about E out. E out was constant. It was 1 or 0, right? All the hypotheses were good on test data. Then we're simply taking union over En of H. Now, our hypothesis class could be infinite. Okay? Now, taking union over all the infinitely many elements is clearly redundant, because En by itself will only have a finite number of possibilities. It is the number of dichotomy vectors which are generated, which is bounded by the growth function. So En is always going to be like a fixed number of values. So taking union over infinitely many hypotheses is redundant. We might as well take just the union over the number of dichotomy vectors we have. This is the intuitive reason why this MH comes up here, because you should only count how many distinct dichotomy vectors are generated. That's the number of En. Now there is a big complication, however, and the complication comes out through E out of H. E out is not fixed, it's dependent on H. It's not random, because for each H, for a fixed Px, there is a certain quantity you generate. But it depends on all elements in X. Like, it does not depend on these endpoints. It depends how H operates on the entire space, right? However, E out of H is the integral of E of Hx and y p of x dx. I shouldn't write the circular integral. It's just like saying integral over the entire space. And this depends on the action of H, not on the using just the dichotomy vectors, but on the entire space X. So here, if I had to compute E out, if I had two hypotheses that had the same dichotomy vectors, they would generate the same value of En of H. However, E outs will be different. So maybe there's a bad event for one of them, but not a bad event for the other, because they had different E outs. As a result of that, this simple idea of taking union over the number of dichotomies no longer works. This E out breaks all the sort of excitement we had. So we have to find a way to fix E out and then prove the theorem. Okay? So it's not just taking union over all the different dichotomies. This is what makes the argument a bit delicate. So we'll start by, again, I'm following the learning from data textbook as it is. All the notation, all the definitions, everything is from the textbook. This proof is in the appendix of the text. So it's an excellent reference to have. Read it. after the lecture. Now, I will make a slight change in notation just to keep things simpler to write. So we have been looking at this events, right? Instead of this is the same as looking at the supremum these two are the same. Okay? Instead of taking the union over all hypothesis when you exceed epsilon, you might as well look at the worst case. You might look at the largest value associated with this difference and see if that exceeds epsilon. These are identical. So if this happens, then at least one hypothesis would have exceeded epsilon. So the supremum would have exceeded epsilon. And if this happens, then clearly one. So this is if and only if. If the largest value of this difference exceeds epsilon, one of the hypotheses would have exceeded, the one that achieves the supremum would exceed epsilon, and so it will be contained in the union bound and vice versa. So instead of having to write the union, I could just write the supremum. It's the same thing. They do that, and that simplifies the notation somewhat, although there's still a lot to write, but I will do that. Instead of the union, I will keep saying the supremum of this difference is greater than epsilon. So this is just a note. This is self-evident. Okay, so now we come to the key lemma. Again, this is from the Learning from Data textbook. So let D prime be an independent data set of n points sampled IID from Px. So we have an underlying distribution Px. Let's sample a new set of n points. So here xi's are sampled IID Px, and the yi's are obtained by assigning the label from the ground truth function f to these. So this is our independent fresh sample of n points. D prime is independent of D, the original set of n samples. So this was our original sample on which E in was computed. D prime is a fresh set of n samples. So now I have two sets of samples of length n each. Okay? Haven't done anything so far. So let me write. These notes will be available later, as always. So define E in prime of h to be 1 over n summation of 1 to n E of h of xn prime yn prime. So we are evaluating our hypothesis class H on D prime, and the resulting error is E in prime. And recall that E in of H is 1 over n summation of n going from 1 to n E of h of xn and yn. This is original training error. Then our claim is that the probability the supremum of E in of H minus E out of H is greater than epsilon, okay, is bounded by the probability that the supremum of over H, E in of H minus E in prime of H is greater than epsilon by 2. This is the claim that we will prove. And the proof is taken from page 189 to 190 in the learning from data text. We'll do it in the class. So what does this say? This is the quantity we were interested in. The probability that the difference between the training error and test error is greater than epsilon. However, this quantity is sort of complicated because it depends on the entire space X. So what we are saying is that if this event happens, then this event, there is a reasonable chance that this event will also happen. That is, if you were to evaluate H on two independent samples of the data sets, one on D and one on D prime, then the difference between these will also be at least epsilon by 2 with high probability. So if there is a bad event that happens here, then a bad event will also happen here. This particular hypothesis class is inherently unstable. If it is going to be deviating from the test error by large on the original data set, then if I were to evaluate this hypothesis on two independent samples of the data sets, my estimates won't be close. They will be further away. So the hypothesis is inherently unstable. If it is going to have a bad generalization error, if I were to evaluate it on two independent copies of the data sets, I won't get answers that are close to each other. They will also be further away from each other. And the gap, there is a small tweaking. Here is epsilon, here is epsilon by 2, and we will do that, like we'll prove that. But this is the intuition, that if H has sort of a is going to cause like a gap between the training error and test error greater than epsilon, then with high probability, if you were to evaluate it on two independent data sets, the estimates won't be close to each other. Okay, that's the intuition. So we'll prove this. The proof is a little mechanical, but you should see it once because a lot of like the proofs in this field are based on similar ideas. Like there is intuition and then you have to combine it with proper rigor to get to the final result. Okay. So we had the intuition coming from effective number of hypotheses, and then we had some stumbling blocks like the test error, and now you'll see how everything gets properly written up. Okay, so we'll start with the right-hand side and start simplifying it. So this is our first thing. Now the reason why this is useful is now we have the training error before I go into the proof. We are computing E in of H and here E in prime of H. Okay? These are both over a total of 2n samples. Instead of n samples, we have n samples here and n samples here. So then we will be able to apply our dichotomy vector arguments on this set of 2n samples and complete the union bound properly. Okay? That's why that we had essentially MH of 2n in this particular statement. This was really coming from the step that we are currently doing. Instead of n samples, we are moving on to 2n samples. Okay, so we'll start with RHS. Let's consider the probability that the supremum is greater than epsilon by 2. Now the way they proceed, I'm going to follow the textbook here. The way they proceed is that they combine this with the event that They combine it with this event. This is the original event we have, and this is the event we want to relate it to. So they start by combining them. So they're taking the intersection of two events. If they have a large probability, this is same as this. If they were identical events, it would be equal. But in any case, we can always lower bound. This probability is lower bounded by this, because here we have an intersection of the original event and some arbitrary event that we have introduced. And now we will write it as probability of the quantity we want times probability of the other event. Given, so this is given, okay, nothing much so far. Just introduce the event we wanted, and then I rewrote this in the opposite way. This is the quantity that we are interested in, difference between the training error and the test error on the data set D. And then because of that and business, I have the other term, probability that E in minus E in prime is greater than epsilon over 2, conditioned on the fact that H is bad. And what we will show is that the second quantity, this quantity is not too small. Meaning that if we had a bad event here, then the difference between the training error between E in on the original data set and the fresh data set greater than epsilon by 2 is large. So we'll show that this conditioning implies this with high probability. For us, we will show that this is greater than 1 minus 2 e to the minus 2n epsilon square. This happens with high probability. Okay? And it's enough for us to see that this is greater than half if n is large enough. Right? Because as n goes to infinity, this goes to 0. But for any sufficiently large n, this quantity will be less than 1/2. And so all we need is some constant. We'll say that this entire probability is at least 1/2. And because of that, we will have shown that this quantity is less than 2 times this quantity, which is what we wanted. So this is what we will prove. Okay. So we want to claim the following. Probability sup h over h given this is what we want to prove, right? Now what I will do is I will prove a slightly stronger statement which will imply this. We will, now this probability is over what? H here is fixed throughout. H is not random. H is a fixed hypothesis. The probability E in here at E in prime are both random because D and D prime are random. So the probability here is over the data set D and D prime. For each age, E in is random because D is random, E in prime is random because D prime is random. Here E out is fixed, but E in again in the conditioning is random. Okay? What I will do is I will actually condition on D as well. What I will prove is, let's call this event E for simplicity, so I don't have to keep writing it. What I will do is I'll consider probability over just the set D prime of the supremum conditioned on the set D and the event E. So I'm going to, instead of taking the probability over D, I'm going to condition over D. And I'm going to show that this is greater than 1 minus 2 e to the minus 2 and epsilon square. So D is my data set. E is the event that for this, once D is fixed, we will have this event or not, right? E in minus E out will be greater than epsilon or not. I'm only going to look at those events over data sets where this happens. So I have a data set D which is fixed, and for this data set, it so happens that supremum of H over H of E in, which is evaluated on the data set D, and E out is greater than epsilon. So this event happens. So I have fixed my data set, and I have said that this data set induces a bad event on H. Then I'm going to say that the same data set, for the same data set, if I were to generate a fresh sample D prime, the difference between E in, which is now fixed because D is fixed, and this random quantity E in prime is going to be large. Is this clear? So I'm fixing my data set. E is telling me that this data set is bad for H, meaning that the difference between the training and test error is greater than epsilon. Now, what I'm going to say next is, if I were to sample D prime at random, and I look at the difference between E in prime and E in, it's going to be large. It's going to be greater than epsilon over 2 with high probability. This is what I'm going to prove. Once I prove this, I can just integrate out over D because the right-hand side is constant and get to the original result. So if this is true, we will show this thing. From here, once this is shown, we can integrate with respect to D on both sides to prove the claim. So I'll multiply by P of D given E on both sides and integrate out P of D given E. That the right hand side is independent, so that integral will be 1. The left hand side will give me my original margin. Okay, so any questions? So now we will do the following. Given D, let H star be any hypothesis such that E in of H star minus E out of H star is greater than epsilon. Since the event E says that there is at least the supremum of this is greater than epsilon, which means that I will be able to find one hypothesis H star in such that when I evaluate it on D, E in of H star minus E out of H star is greater than epsilon. Right? So given D, let H star be any hypothesis in H such that E in of H star minus E out of H star is greater than epsilon. This I can always find by definition since event E guarantees that this happens. Okay, then instead of looking the supremum over all H in the left hand side, I can consider the following. The left hand side is lower bounded by the probability that E in of H star minus E out of H star or E in prime is greater than epsilon by 2 given the events D and E. So instead of looking at the supremum over all H for which this event happens, I can look for just one particular hypothesis that satisfies this. So this hypothesis is bad between the training error and the test error. Right? This hypothesis H star is bad for D. What we are now saying is that this hypothesis will also be, no matter if I select D prime at random, this hypothesis, so the only randomness here is in E in prime of H star because this is evaluated on D prime. So I'm saying that so this random variable will be larger than E in of H star so that it's greater than epsilon over 2 with high probability. So the deviation between this greater than epsilon over 2 has a high probability. So I'm now fixing D and right the data set. From that data set, I get one hypothesis H star, which results in a bad event over D. This hypothesis will also be having high fluctuations when I select D prime at random. So this hypothesis will have this property that E in prime of H star minus E in of H star will be greater than epsilon over 2 with high probability. This is what we are showing. If we show this, then the supremum only helps us here. So we'll get a lower bound and we are done. So our claim is that this quantity is greater than 1 minus 2 e to the minus 2 and epsilon squared. This is what we are going to prove, that this quantity is greater than this. So to do that, we want to use the property in the conditioning. We want to use that this is large. So this cannot be, so we want to somehow put that in here. And so for that, we can show the following. Our claim is the following, that if I look at E in of H star minus E in prime of H star, this is greater than epsilon minus E in prime of H star minus E out of H star. This is what we will show. What this is saying is the difference between these two cannot be too small. It's greater than epsilon minus the difference between E in prime and E out. So how do we show this? Well, we will use the triangle inequality, simply. we'll add and subtract this quantity. Okay. This I can write it as E in of H star minus E out of H star minus E in prime of H star minus E out of H star. Okay, the same thing, just algebra here. And now I use the fact that the absolute value of A minus B is greater than the absolute value of A minus the absolute value of B. Okay. Now what do I know? Well, I know H star has the property that this difference is greater than epsilon. This was the conditioning event. E event guarantees that E in of H star minus E out of H star is greater than epsilon. So this is greater than epsilon minus E in prime of H star minus E out of H star, which is what we wanted to prove. So this is a style of proof you have to prove in learning theory. So I'm going to do one so you get an idea of like the kind of tricks they use. Many of the proofs that they do are variations of these kinds of arguments. So it's good to see them at least once. Okay, so what we have shown is that this quantity which we wanted to bound is greater than epsilon minus this quantity. So what I wanted to consider was probability that E in of H star minus E in prime of H star, the difference of the errors, training errors on the two quantities, given D and E. This is what I wanted to bound, right? Now, what I know is that this quantity is lower bounded by this quantity. So instead of the original probability, I can require that just the lower bound is greater. So if I will take epsilon minus E in prime of H star minus E out of H star. This quantity is greater than epsilon over 2 given D and E. So this is a lower bound because if this event holds, then clearly this quantity will be greater than epsilon by 2. This quantity is smaller than this quantity. So if this quantity is greater than epsilon by 2, the original event will be greater than epsilon by 2. Right? So if I am trying to just consider the lower bound greater than epsilon by 2, then that probability clearly lower bounds the original probability. This only has higher probability because this quantity is always greater than this. So if this implies this, but other way is not true. So I can look at the lower bound, and so this requires, this is the same as saying probability of D prime E in prime of H star minus E out of H star less than epsilon by 2 now, because if I bring this on the other side and do the algebra, conditioned given D and E. This is what I want to bound. So D prime, the probability is over D prime, which is a fresh sample independent of D. There are n points selected independently of D. E is an event that is a function of D. It's saying that there is a hypothesis where D makes it a bad event. That if you evaluate E in minus E out for that hypothesis, it is greater than epsilon. So this H star is a function of D as well. It's selected based on D and so on, right? It's a bad hypothesis for D. Now, what I'm doing is I'm evaluating H star on a fresh sample of D prime points. I'm going to compute E in prime and see whether the error here is far from the test error of H star, the expected value of this of E in prime. And I want the probability of this to be less than epsilon over 2. So remember, H star was selected in a very complicated way after looking at D. D is our one set of sample. H star was some complicated function of D. Okay? But H star, as far as D prime is concerned, is a fixed hypothesis. D prime was sampled completely independent of D. So when we are trying to evaluate E in prime minus E out with respect to D prime, H star can be thought of as just some fixed hypothesis. We did not look at D prime when selecting H star. And now we are asking, what's the probability that our estimate of E in prime on D prime for H star is close to E out of H star, the test error of H star? Do you think this will be large or small? Will E in prime be close to E out generally, or will it be far away? The training error. Okay. Now I'm going to compare. If n is large, this will be basically close to E out. This is a fresh set of samples. I'm going to evaluate the hypothesis on this, get an estimate of the, or compute the training error. It will be close to H star, E out. What sort of inequality will make this clear? What inequality can we use here? The Hofding's inequality, basically the Hofding's inequality says is because the randomness is over D prime, it is independent of these events, we don't have to worry about it. H star is some fixed hypothesis, and by Hofding's, this is greater than 1 minus 2 e to the minus 2 and epsilon square. Because the probability that this is greater than epsilon by 2, okay, maybe I didn't get epsilons right. Epsilon by 2, right? So this I have to fix here as well. So this probability has to be large, and Hofding says the opposite, that the probability this is greater than epsilon over 2 is less than this quantity. So I'm just flipping it over and saying that this has a high probability. So this is, maybe my constants might be off because of this thing. That's okay. Okay, so this is what we have now done, summary of what we have shown so far. So the point is that this is greater than 1/2 for n large enough. Doesn't matter what these constants are. If n is large enough, this quantity can be made as small as possible, so it's greater than 1/2, right? So what we have now shown after all this discussion is the following. The probability that supremum over H of E in of H minus E out of H is greater than epsilon is less than 2 times the probability of supremum over H that you have a deviation in the training error over 2 independent samples. This is the first half of the proof. So this was sort of, we wanted to get rid of E out because E out was an integral over all the entire space. There was no way to put in dichotomy vectors in E out. So we got rid of it at a small price. We have a factor of 2 in front and we reduce epsilon by epsilon over 2. So that's the first part. From here, we will now move on and use sort of the argument of dichotomy vectors. So now let S be union of D over D union D prime. Be the union of all data points in D and D prime. Let HS denote the dichotomies generated by H over S. So now we can now introduce a dichotomy sort of counting argument in this sort of for this event, right? So let's say D union D prime be the collection of all the data points. It will be 2n data points. HS denote the dichotomy vectors. Then and let the size of HS equal m. That there be m of them. M dichotomy vectors in this set. Then m is guaranteed to be less than mh of 2n, right? This we know by definition. And suppose the dichotomy vectors in HS are achieved by H1, H2 up to HM. Suppose these are the hypotheses. Each dichotomy vector has to be achieved by some hypothesis function. Let's say H1 to HM achieve it. Then we will just for to make things completely rigorous, we'll consider the following probability. There is one more complication that happens. So dichotomy vectors are functions of the data points. And so if you want to define them, you have to fix the data points. As a result of this, we will have to define all events conditioned on this set S and then integrate out. Okay, so we are interested in this. Let's consider this event. The supremum over all H of E in of H minus E in prime of H greater than epsilon over 2 conditioned on the set S. Now, what is the probability with respect to? In this event, when we compute the probability, we'll consider all random partitionings of S into D and D prime. Here, if we had fixed S, then, and if we had sort of fixed it, the first n elements belong to D, the second n elements belong to D prime, this is not a random quantity. This is a deterministic quantity. So to avoid that, this probability is over random partitionings of S into D and D prime. So we will take n elements from S uniformly at random and put them in D, and you can put the remaining in D prime if you like. So S fixes, S is a set of 2n elements. Okay, that's fixed now. For this, we will take n and put them in D, and we'll take the remaining n and put them in D prime. This is...
I have a bit of confusion here because so D prime is supposed to be selected independently of D.
Yes, yes.
Does doing this cause any problems? Does it make, because now D prime cannot, none of the elements in D, they're disjoint now, right? That's guaranteed.
Yeah, so if you assume S is selected IID, the samples of S are selected IID, then the fact that you have seen the first n element of S and put them in D will tell you no information about the elements.
Okay, then S is not a set, right?
S is a set of 2n elements.
Yeah, but sets are sets. You can't have the same element in a set twice, right?
You can have. Or?
In a set, you can't.
So S is just a collection of points. So yeah. PS, so S. I'm going to say S consists of x1, x2, up to xn. This, right? And each element is sampled IID px.
Okay.
This is what I defined. Yeah, you're right. There's a small probability they will be identical, but for real cases, it's not important. And the idea is I will take I will fix, if I fix S, then I will take n points at random, put them in D, and I will take the remaining elements and put them in D prime. And because I have not seen these elements that I put in D prime, this will preserve the mutual independence between D and D prime. That's a good question.
To avoid this confusion, can we just see S as a vector, the random vector?
Oh yeah, sure. You can. Yeah, the set, when I said it was a collection of elements, but you're right. Strictly speaking, the set means that if two elements are identical, so you can think of it as a vector. In practice, it won't matter at all because the probability of those sets with duplicates is 0, right? So because all the xi's are in RD. But sure, if you like, you can think of them as a vector, and each element from the vector is included in D with uniformly at random. Okay, but the reason why we have to condition on S is that now we can say that we can apply the dichotomy argument. So this is saying the probability of the supremum, instead of taking the supremum over all H, I know that for any given S, E in of H and E in prime of H can now be defined, can have only so many values. So if I fix S, I know I have x1, x2 up to xn, some collection of vectors, some collection of data points. Now the total number of values E in and E in prime can take here is now given by the dichotomy vectors, right? So I can write this as the supremum over all H in H1 to Hm that achieve the dichotomy vectors of So because all the dichotomy vectors can be generated by this set, H1 to Hm, these are the hypothesis functions that were generating the dichotomy vectors. Instead of taking the supremum over every element in H, I can restrict myself to supremum over those hypotheses that generate the dichotomy vectors. Okay? This is just saying that we can replace this supremum by this, because E in and E in prime will all be computed by this collection of hypothesis functions. You don't need to take overall H. So we can apply a union bound to this now. So now we can use the union bound. And what we will get is that this is upper bounded by the summation of I going from 1 to m, probability of E in of Hi minus E in prime of Hi greater than epsilon by 2 conditioned on S. The supremum is like a union of events, right? This supremum is the same as we argued before. It's like taking the union over H1 to Hm. And once we have the union, we can apply the saying that if this event happens, then one of the HIs should have a bad event. If we evaluate this. So instead of this supremum, we can apply the union bound like this. And you can upper bound this by M times the supremum over H in H1 to HM, probability E in of HI minus E in prime of HI is greater than epsilon over 2 given S. Okay. Now M is upper bounded by MH of 2n. I have the supremum over H. I can just write it here as the supremum over all H in H. This doesn't change anything. And instead of this S, I can take the supremum. Instead of a fixed rank, like given S, I can further take the supremum over all S that was generated. Oops. So now I'm not going to consider a random S here. I'm going to look at the worst possible location of two endpoints. Okay? From these two endpoints, I'm going to put n of them at random in D, the remaining go in D prime. Here I'm allowed, because this is a bound, I'm allowed to change my distribution. So I'm going to say instead of taking a random S, let's look at the worst cases. So fix two endpoints, put n of them in D, put the remaining in D prime, that's where the randomness comes. And I'm going to say, hey, what is for, let me look at E in and E in prime, and let me look at the worst hypothesis that for which this is greater than epsilon over 2. So this is the quantity that we now need to bound. Okay. So we are out of time, so we'll have to do this next lecture. We'll continue from here. I know this was a little bit dense, and so I highly encourage you to read the appendix in learning from data text to sort of fill any gaps you may have during this lecture. I'm myself teaching this for the first time, so it might not be the most polished way I'm explaining things. So